I got a lot of content, so I'm going to run a timer, and I'm going to run a timer on here. How are we all today? Who had a blinder last night? I went to Botswana Butchery and had a meat coma. It was fantastic. There are many ways to skin the cat when it comes to sticking your data into Windows Azure. And this session we're going to try and really run around a whole lot of different approaches. So we're not going to go particularly deep on anything. We'll probably go deeper at the start, lighter at the end. But hopefully everybody's going to learn something new today. And in many ways it's a case of trying to help you, find out what you don't know about, so you can maybe go and do a bit of exploration about some alternative approaches. So before we start, let's talk a bit about why we actually go and use the cloud. I'm not going to do a whole lot of introductory content here. I'm going to assume you all have a pretty good idea of what the hell cloud computing is, what Azure is, what Amazon is, blah, 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 blah. But really, down here in Little, you go to big overseas conferences and all they want to talk about is, whoa, we're going to build this massive high-scale application in the cloud. And down here in little old New Zealand, you kind of need to have a slightly more nuanced view. So the cloud is really fantastic for building these massive distributed applications, right? Distributed systems, a big application is going to run across multiple machines, whatever you do, right? The old one box no longer works. You're going to be programming against some sort of abstraction layer, right? So you're going to basically take the interface that is given to you by the cloud provider and you're going to program against that. And you're going to try and discourage yourself from wanting to spelunk below that abstraction layer, right? You want to look at the abstraction layer, the interface you're given, and not try and work out how it works underneath, because they're going to be able to change that. They want to be able to change it over time, all right? As things improve, they change it over time. Good example, Windows Azure Storage, right? About mid-2012, they flipped a switch on Windows Azure Storage about the 7th of June, and basically doubled the speed and completely changed the way it worked. Bless them, they did not automatically upgrade your storage account. So if anybody's still got an application deployed on a storage account that they created prior to June 2012, you might want to have a little look at that and go and change it out. Runs on commodity hardware, right? And the cloud provider takes care of making all the pain and crap that comes with dealing with commodity hardware go away, right? So if you have to use commodity hardware yourself, you've got to deal with the failures and how you manage it and bloody blah. They take all that away and deal with it for you. The reason they can offer you such good pricing is they use hardware that's a couple of generations old, right? And ultimately it's going to be composed of multiple services, right? Some of the platform services that you buy from the cloud provider, some stuff you're going to get from others, so other people's services, and then some stuff that you write yourself. So that's a really important use case, right? Building big-scale applications. An equally important use case is thinking about using the cloud as a low-cost and really capable platform for deploying your application. Right, now, it's not the cheapest platform, right, but you get to leverage some of those benefits that those cloud providers are driving in terms of economies of scale, right, such that as a smaller dev shop, a small enterprise corporate, you can deploy your application into really top-class data centers with really good levels of availability for a really low cost. And it's important to know which of those sorts of scenarios you're leaning towards, right? Because you probably don't want to go chasing, I'm going to build this massive high-scale application. Well, yeah, that's great. But if you do that, you're going to pay a big price for it at development time, right? Because you're going to lose many of the, the really mature, really easy to use tools that we've been able to use over the years, and you're going to have to start, building the system that's a bit more of a science experiment, a bit more cutting edge. Right? You're going to have to make some trade-offs that you might not have to make if you say, actually, I can get away without partitioning my data. Right? Single SQL box, good as gold. So, with that, let's do a bit of a sort of a trip around some various storage options for Azure, because ultimately storage is the hard bit in any distributed application. Heaps of seats this end, guys, right down the end. Right? Storage is hard. Stateful is hard. Not stateless is easy. Stateless is an absolute piece of cake. Right? We can scale that out till the cows come home. Stateful, very hard. Transactional, very, very hard. Right? Transactions do not scale at all. Right? Consistent transactions do not scale. So, Azure Storage is really the fundamental building block of any application that we're going to build up in Windows Azure. It is a durable, stateful, highly available storage layer, and it basically underlies most, though not all, of the storage approaches that we're going to discuss today. The one it doesn't underlie is a thing called SQL Azure. So SQL Azure runs on its own servers, and it actually stores the databases separately on the metal in the individual machines, rather than using some other storage approach. Otherwise, for everything we're going to talk about today, if the storage is durable and going to something that's not going to go away when you turn the power off, it's going into Windows Azure Storage. So Windows Azure Storage works by replicating the data that you write across 3 consistent replica copies in a given data center. And then you have the option of also having that data asynchronously replicated across to another data center in the region. You pay a bit more for that. It's on by default. There will be times when you don't want to do that. So a good example of where you'd turn that off is if you decided you'd run your own database platform on top, say you ran React or Mongo, and you handled that geo-distribution yourself. Right? So actually you say, I'm going to do geo-distribution myself. So if I've got some data in Singapore and some data in Hong Kong, and I'm doing the replication, there's absolutely no point in paying the extra cost to have that replication also happening at the storage layer. This geo-redundant thing, it's not like, you know, you've got a copy that you can easily go and grab in that second data center. This is really for the, oh dear, a nuclear weapon has hit the data center. What am I going to do to get my data back scenario? Right? You know, it's not like a classic, it's not a backup. Right? It's a replica in case something goes really, 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 really wrong. And at the moment, the process to get that back and spun up in the second data center is a very manual process. It's shell out to support. In terms of capacity, everything's driven around this idea of a storage account that has some limitations placed on it. Actually, these limitations are a little softer than Microsoft might admit, because I've recently learned that if you're prepared to buy more than a petabyte of data, you can actually have more storage on a given storage account. I'm not sure anybody who's prepared to necessarily... Anyone using a petabyte of data yet for any of their applications? No, didn't think so. All right, so otherwise, you're basically stuck with these limits. All right, so we'll talk a bit about how you get around those later. The key thing to watch for with Azure Storage is really latency. Right? Because this is a virtualized storage subsystem. Ultimately, every storage call is going across a number of network hops in order to actually land into some sort of durable storage. Right? So if you were to compare this against, say, hard drives on a local machine, much higher latency. Can achieve very good throughput, and we'll talk a bit about that shortly as well. You get 5 storage accounts per subscription. That is a very soft limit. No problem with you calling up saying I want more storage accounts, and there are really good reasons to do that. So, costs. You pay for your storage, really 2 main things you're paying for. The first is you're going to pay for how many bytes you're storing on disk, right? And that's slightly different between geo-redundant and non-geo-redundant. Gets down to anywhere sort of around 4 cents US a month. Remember, that is triple replicated storage. Anyone think they can do that cheaper on their on-premise SAN? Right? No. So, in fact, it's actually interesting. One of the offers that Microsoft have is a thing called Store Simple. There's one sitting down in the exhibition area at the moment. It's basically a thing you chuck in your rack. It's like basically a SAN with a final tier of storage going up into the cloud. Well, worth going and having a bit of a look at that if that sort of stuff floats your boat. So you pay for your storage. That's pretty easy to understand. You also pay for transactions into and out of storage. So basically all the calls that you make to the storage service. And they meter that by watching your calls to the RESTful web service that is your route into and out of that storage account. So a transaction is basically a call to that service, regardless of what actually happens under the hood. Right? And that's quite different to someone like Amazon. Right? So if you compare Windows Azure Table Storage to Amazon DynamoDB, right, DynamoDB, you have to understand what happens underneath the curtain, right? Because your transaction billing there is how many table records you hit, whereas your transaction billing here in Azure is the fact that you've made that one REST call. If you touch multiple table records in a single REST call, one transaction in Azure, potentially up to 100 to 300 transactions in Amazon. This stuff used to be very significant. It's got a whole lot less significance since they dropped the price tenfold by taking it from 1 cent per 100,000 transactions to 1 cent per 10,000 transactions. If you have a really chatty application, it is still worth doing a bit of a quick back-of-the-envelope model of this, because I can certainly show you some models where it is a very, very significant cost in the overall application running cost. Pushing data into and out of the data center, you pay for data egress. So data out of the data center, you do not pay for data going into the data center. Slightly different price depending on whether you're in the US and Europe or whether you're in Asia, so basically Singapore or Hong Kong. A few tips on storage. We need to distribute our data requests across partitions, and we'll talk about exactly what a partition is shortly. And what a partition is differs a bit between the different storage abstractions that we're going to see. Make sure you perform your one-time ops at setup times. If you're going to go and create queues and all those sorts of things, don't try and do that in a lazy fashion, right? Go do it once, keep a track of whether you've done it, don't go and try and do it again, because it's expensive to make that round trip across the network. If you go and end up doing that every time you go and hit the storage endpoint, it's going to be really, really costly to you from a latency point of view. Use appropriate retry policies. This stuff is a shared service. Sometimes it slows down, sometimes it has a few little hiccups. If you're seeing that, you're going to start getting 503 error codes coming back. You need to back off and then slowly reapproach the service. So you've got to do a bit of smarts in terms of how you consume this, and there are some libraries available to help you do that. Hopefully it goes without saying, co-locate your storage and your compute in the same region. So if you've got a web server and you're hitting an underlying storage server, don't stick one in Hong Kong and one in Singapore, all right? There's a little latency gap between the two. You also have to pay for the traffic, all right? You kind of don't want to do that. So stick them in the same region. There are occasionally, reasons to go otherwise. Ultimately, the storage service is just a RESTful endpoint, so you can hit it from wherever you want to, right? We could pull up the endpoint right here and start poking data into Singapore, piece of cake. In terms of scale out, right, you're scaling out by scaling out across multiple partitions. At some point, you're going to hit that 20,000 operations per second limit on a per storage account basis. At that point, scale out across multiple storage accounts. Right, you will not be, if you can scale out across multiple storage accounts, you will not be able to saturate Windows Azure storage with throughput. Right, your credit card will not withstand saturating Windows Azure storage with throughput. Use a different storage account for diagnostics. Again, it's completely separate data. It has nothing to do with your application, so stick in another storage account and don't consume any of that 20,000 transaction limit. So when we work with storage, we have these 4 abstractions, right? Ultimately, these all map down to the same underlying storage infrastructure, right? So under the hood, they're all basically the same. They're just exposed to you as different types of services, and they meet different sorts of needs. Blobs, pretty much a simple file storage endpoint. All of these things are RESTful services, but in the case of blobs, you use it as a RESTful service, right? You go do a get at the endpoint, you get a file back, right? Disk drives, you probably don't go and do a get at the endpoint and get a file back. Right? Well, you absolutely don't, right? Because effectively you've just got pages of file pages. Tables are basically a key value store, a highly scalable key value store. Queues, we're not going to talk about at all today. And we're going to go and drill into each of these in a bit more detail. I've got a few important concept slides through here. And important concept number 1 is that you can't travel faster than the speed of light. And what I mean to say there is your durable storage is always Windows Azure storage. Now, you may think that you're a rock star and you can come up with a better way of consuming Windows Azure storage than table storage. But actually, I think if you want the fastest possible key value store that is durable on Windows Azure, you're probably going to want to go and use Windows Azure storage, right? Unless you're going to go and make some other trade-offs, right, in terms of consistency, in terms of overall availability and so forth. Right? Because at the end of the day, you're writing data. If you want that data to end up on disk and you want that disk to be durable, it's going into Windows Azure storage. Does that make sense to everybody? Right, we just can't store data faster than this thing can stick it on disk. So the design goals of Azure storage. Highly available with strong consistency, right? And that's actually quite a hard thing to do, right? So it's designed to, if people are familiar with the CAP theorem, we're going to talk a bit about that later. It really focuses on availability and consistency and partition tolerance to certain types of partitioning. To be durable, right? So when we do a write, it is a durable write. It is strongly consistent across those three replicas. Those three replicas are durable writes. And to be scalable, scaling up to zettabytes and to millions of concurrent I/O transactions per second. I think, at last check it was running at about 900,000 transactions per second. If you kind of like to geek out on this stuff, there's a really good paper showing exactly how it works under the hood by the chief architect, Brad Calder. It's well worth going and having a read. There's a paper, there's a video, there's a slide deck that you can go and have a look at. So as I said before, Azure storage is basically the same under the hood underneath those abstraction layers. So whether we're using queues, blobs, tables, disks and drives, it actually looks the same underneath. So it uses a distributed file system at the very base, and that is an append-only file system. So it's a highly efficient write-optimized append-only file system. So those writes go onto SSDs, right, and then get sort of picked up and moved into slower and lower cost storage from there. So, you are writing to SSDs when you write to Azure Storage. And it's that distributed file system that actually does the triple replication. We have this thing called the partition layer, and the partition layer basically provides the transactional semantics for those various abstractions. And it's the layer that chooses exactly how to go about storing this data into that distributed file system. It provides the replication across different geographies. And it really owns ensuring that we maintain consistency. Right? VFS ensures that we maintain availability. This ensures that we maintain consistency. Right? And then the whole system is tolerant of certain types of partitioning as between those two systems in terms of failures of certain types and network racks and so forth. So if we think of something like a Windows Azure table, we're ultimately going to split that up, and these servers here are responsible for a portion of that table. Right? They don't store a portion of that table. They own the overall consistency for that table. The data is ultimately stored down in that distributed file system. Right? But what it does mean is that if we have a failure of one of these nodes, we have a Paxos master system, right? So a multi-node master system. It can then move responsibility for that partition to another partition server. If one of these partitions gets particularly hot, right? Maybe the Miley Cyrus partition, right? The Miley Cyrus partition got pretty hot a few weeks ago. Right? We didn't know that the Miley Cyrus partition was going to get hot a few weeks ago, but it did get hot. When a situation like that happens, right, what the fabric will do is it will actually move other partitions that have been served by that partition server off that partition server so that you get a bit more dedicated resource. Right? The data is not being moved. I want to be really clear about that because it's really easy to confuse. The data is staying exactly where it is, but the partition server that's serving those requests is being moved around in real time. The data is moved around on a lazy basis, right? But this stuff is actually optimized in real time. So I promised that we're going to do 12 different storage approaches in the course of this session. This is number 1, blob storage. Pretty bloody simple, right? Blobs are stored in a container. The blob storage is a RESTful endpoint. You can put blobs and they go and land in the RESTful endpoint. You can get blobs and they get served back out to you over HTTP from the RESTful endpoint. Very, very nice, right? Super easy to consume. You put blobs into containers. Your scoping and your authorization is at the container level, but the container is really logical only. Your container doesn't have anything to do with the overall scalability of the system. Your scale point is a blob. So if we think back to that idea of partition servers, right, the partition point for blob storage is a blob. Each blob will do up to 60 megabytes of traffic outbound on a per blob basis. If you find that you're going to exceed that, you're going to need to duplicate that blob and scale out over either multiple blobs or potentially multiple storage accounts. A couple of different types of blobs. You have page blobs and block blobs. Pages are really optimized for random read-write. Blocks are optimized for uploading contiguous file extents and then committing those file extents. And if you go and read that paper that I pointed to you to before, you'll see that at the end of the day, the block stuff actually maps down to the way the underlying distributed file system works in terms of its extent writing approach. Blocks are correspondingly a faster way to work with the service. Page blobs are set up as sparse storage, and the benefit there is that you can use those for things like VHDs, where potentially a whole bunch of the VHD file is zeroed out space, and you don't want to pay for that piece of zeroed out space. As said before, it's a RESTful endpoint. You can hit that RESTful endpoint direct from your client. So blob storage is a great place to put things like the images that sit behind your website, right? Because you can send the client straight to the blob store to retrieve the data over HTTP rather than having to proxy that data through your web server. You can pick up a whole lot of load off that web server and stick it straight into blob storage. You can also use a thing called shared access signatures, and they basically let you create a digitally signed URL that can give a consumer a time-bounded write permission set for a particular container or a particular blob. Right? And then Azure also sort of supports a CDN, and we'll see why I say sort of shortly, that you can configure to sit in front of blob storage as well. So a quick worked example. So say you've got a photo video upload site, global audience, uploading big files. How might you approach this? So the first thing I think about is I kind of want to keep the load off my compute servers because compute's really expensive. So let's get them directly uploading that data into blob storage. We can do that by either using a JavaScript client library or even better, a Silverlight client library, and uploading that data directly using a shared access signature into the blob store. And there's a way to do that with JavaScript there. And there's a way to do it with Silverlight there, which is both pretty easy to do. Take account of the geodistance, right? So send consumers to their nearest possible storage server, right? Therefore, send to the nearest possible Windows Azure data center around the world. So basically upload into different data centers. If you need to scale out because you're hitting traffic limits, use multiple storage accounts per geography. And I would probably think about using non-geo-redundant storage for that ingest process, and then go in and potentially picking up and batch processing those files into geo-redundant storage as part of some sort of background process. So you'd probably process that data with compute co-located with each of those storage accounts, and then probably avoid pushing those large files back out over the network. So then push the processed file into geo-redundant storage. You might want to think about gzipping the content, right? So blob storage supports gzipping content and setting the appropriate compression headers on the file when it's sent back to the client. So that's going to save you some space, and it's going to save you some outbound traffic. And then deliver that content back out over the CDN. Is anybody doing something like this at the moment? Nobody. Is anybody using blob storage at the moment? 2 people. Is anybody using Azure at the moment? 3 people. Wow. There is some huge opportunity to do some really cool stuff in this room, folks. Got a bunch of talented people with this awesome tool at their disposal. So hopefully you're going to be able to go and do some cool stuff after this session. Azure CDN. Who knows what a CDN is? Cool. It's the thing that speeds up watching the video from the Olympics. Basically what it does is it caches content out at the edges of the network. So if I'm watching the Sochi Winter Olympics, because I'm kind of into skiing and things, I can either be watching that by streaming the video content from Sochi, Russia, right? Or that video content could potentially be being pushed into a data center, say in Sydney or here in Auckland, and I could be watching that content coming out of Auckland or Sydney, right? So a CDN is basically responsible for geo-distributing a particularly important, particularly heavily used data set to data centers around the world, and then intelligently routing through the DNS system clients to that specific server, right? So basically what the browser client does is it's going to look up by URL, it's going to hit a DNS server. The DNS server's got some smarts in it. It's going to work out the shortest or the closest node, right? Really the least expensive node for you to get to. It's going to then send you back an IP. You go and hit that node. That node's going to say, is the data in my cache? No, it's not. It's going to go to what we call the origin server. In this case, blob storage or say a Windows Azure Compute node web server. Going to bring the content back, store it in the cache, send it back to the browser. Right? Same thing happens again for additional clients. It's going to go and pull it from the cache. It's never going to have to go and touch the origin server until the cache expires. Right? Much lower latency for your clients, far less load on your origin servers. Improved scalability, improved overall experience. There's a bunch of nodes in the Windows Azure CDN spread around the world. And in terms of costs, it's a little cheaper to serve it for the rest of the world, and it's a little more expensive to serve it for EU and the US when you compare it to just serving it straight out of blob storage. A few strategies here, right? How you might use this is really good stuff. Unfortunately, it's a little funky in that you can't currently get your hands on it because they've sort of semi-grandfathered it, not taking any new customers. And hopefully they're going to, I think inevitably they're going to bring out a new type of offering in the next wee while. But at the moment, unless you already have a CDN account configured, I don't think many did, you're not going to be able to get your mittens on it. But when you can, serve your blob content, right? Pretty simple. Got content in blob storage, push it through the CDN. Serve content from your hosted services, right? JavaScript files, blah. You've got them sitting on your web server, route that data through the CDN, take the load off your web server, get the files closer to your client, reduce that latency hop, improve the overall experience of your users. And if you want to be really clever, you can also use this to serve content from your on-premises apps. Now, you can't currently set it up so that your on-premise server is the origin server, which is what you'd really like to do, and hopefully they turn that on. But you can at least push the content from your on-premises server into blob storage and then serve up MSCND URLs off your on-premises server so that all of your static stuff is being served up off the CDN. Anyone doing that at all yet? No. One? Yeah. It's great, right? It's cheap, crazy cheap. Heaps cheaper to buy traffic from here than to buy it from shipping it out of New Zealand. Tables. So tables is our third option. Tables is a NoSQL key value store, right? So we basically store things called entities and tables. An entity is like a flexible property bag. There's no fixed schema. You can basically stick whatever the hell you want into your table. Who's that? No, that's not me. No, that's good. Thought my time was up. I was freaking out. It would have been a real problem because we're only up to number 3. Tables, every entity has a thing called a partition key. The partition key, surprise, surprise, determines what partition it sits in. That partition does map directly down to a partition server in the partition layer of Windows Azure Storage. Right? So you kind of need to know a little bit about what's under the abstraction. Right? There's no guarantee they'll always do that approach, but it is worth knowing. Right? Because it does mean that if you're doing batch operations, you really want to include the partition key in your query as much as possible. Your unit of scale is the partition and then the storage account. The table has nothing to do with scale. You are not going to get more scalability by creating more tables. You are only going to get more scalability by creating more partitions, and if you run out of that, right, because you're hitting 20,000 operations per second, by creating more storage accounts. It's unlikely you will hit 20,000 operations per second because that will mean that you are accounting for 5 or 6% of the overall instantaneous traffic on the Windows Azure Storage platform. And again, you must have a really good credit card. It's not a relational database management system. It does not have all sorts of nice things like atomicity, consistency, isolation. It does have durability, all right? So don't normalize your data. store different types in the same table. Be careful with your queries. Those large scans where you're not including the partition key are very, very expensive, both in terms of time, latency, and transaction costs. Embrace eventual consistency and basically groom your data. Right? So be prepared to stick data into the table storage, and then in the background batch process that data to come up with the data set that you ultimately want. I'm not going to drill on this in a whole lot of detail, right? Because you're all going to go to AZR 412 this afternoon, where Steve is going to talk you through this in a whole lot of detail. Approach number 4, drives and disks. All right? Basically sticking a VHD file in a blob and then attaching that VHD into Windows Azure's compute service, right, such that you can run Windows or Linux or a range of other things against that VHD. You basically upload a fixed style VHD format into a page blob, and off you go. You can't use dynamic VHDs, you've got to use fixed VHDs, but because we're dealing with sparse storage, you're not paying for the empty space, right? So even if you're only going to use 20 gig, upload a 200 gig, right, fixed blob, so that you don't end up running out of space. Drives and disks are slightly different. And the reason drives and disks are slightly different is that Windows Azure Platform as a Service, right? So Windows Azure Services uses drives, and it has a slightly different approach to how the driver works as opposed to Windows Azure Infrastructure as a Service, so the thing that came out recently. Right? Windows Azure Infrastructure as a Service uses disks, and it has a slightly different approach. The difference is really that in PAS, the driver sits inside the guest operating system. In IaaS, the driver sits inside the host operating system, so the guest operating system sees the hypervisor exposing a standard PC storage interface to it. Right? It means it's much easier to achieve higher levels of compatibility here in IaaS because it just looks like a bog standard x86, x64 machine with a storage interface on it. So, drives, the driver sits in the Azure guest operating system, and then the REST traffic goes off that guest operating system out to blob storage. Disks, the driver sits in the Azure IaaS host operating system, and the traffic goes out of that host operating system. One thing that's worth noting is that drives, everything is done in 128 kilobyte chunks. Disks, everything is done in 2 megabyte chunks. If you have chunky I/O operations from whatever you're running in that virtualized machine, then you probably are going to see some cost savings in terms of your transaction traffic by using disks over drives. The question, and I tried to answer it yesterday, but I couldn't get SQL I/O to work on the Azure instance I was running, is whether we think disks and drives are going to deliver different levels of performance on account of their different paths to hit the storage endpoint. So if anybody wants to have a quick stab at that, you just run SQL I/O up in each of those different machines. For some reason, I ran SQL I/O up and it kept on crashing on me, and I couldn't work out what the hell was going on. So everyone knows what SQL I/O is? Yeah? Yeah, it's basically a way of thrashing the crap out of your disk subsystem. All right? How fast is my disk subsystem? SQL I/O will tell you. All right? If you want a really fast disk subsystem, I highly recommend trying the solid-state drive in your laptop. It's really fast. So, it's often faster than many of these cloud providers can achieve for you. One other thing that's important to note here is that you can get away with mounting more drives into PAS than you can with IaaS for the same size machine. Right? So with IaaS, you basically limit it on the number of drives you can mount based on the size of the virtual machine you're working with. And that can be important if you're in a really disk I/O bound scenario, and basically you need to try and get the maximum number of I/O operations possible out of the thing. Caching. So it's important to think about caching. Both disks and drives have an ability to use a local cache to change the way that you access storage. It's not necessarily going to be faster, because it's really a trade-off, right? You're trading off I/O operations, latency, and cost. If you cache it, right, you're going to get lower latency because it's closer to you. It's either on the local drive or in memory, right? You're going to get lower costs. You're not incurring storage transactions. You are, if you're hitting the disk cache, going to get lower IOPS, because the IOPS that you can get off a disk drive is lower than the IOPS that you can get, albeit at a higher latency, off the Windows Azure storage endpoint. For most online transaction processing style database scenarios, which I'm guessing is probably the common scenario for most folks in the room, you probably want caching completely off. So going straight through for high IOPS, random I/O into Windows Azure storage. So an important concept to take away, right, that the performance limits on Azure storage are entirely artificial. You are limited only by how much money you are prepared to spend, right, because you can scale out over multiple storage accounts. Each drive will potentially give you 500 IOPS. Right? You can have a lot of storage throughput. Right? If you can design your data abstraction layer to be cognizant of multiple storage accounts, you can design a data abstraction layer that has scalability that is bounded only by budgetary constraints. But again, remember that first important concept, which is if you don't need to build a really scalable system, don't go and build a really scalable system, because it's complex. Is there something equivalent to the CDN for tables? There is nothing equivalent to the CDN for tables. No. If you wanted to do something equivalent to the CDN for tables, what you'd probably do is either use one of the things I'm about to talk to you about, or use some other caching mechanism. Maybe slap the data into memcached or something like that. Right? There may be scenarios where actually you're prepared to sacrifice durability, where you wouldn't use tables at all. And actually, we'll talk about something just like that shortly. Relational databases. I'm going to move super quick through this because this should be teaching you all how to suck eggs. Two options for relational databases. Windows Azure SQL Database, formerly known as SQL Azure, and certainly preferred to be known as SQL Azure by me. That SQL server dished up to you as a platform as a service offering. You pay as your money. You get a logical database server, you go create database, it gives you a database back, and Bob's your auntie's live and lover, off you go, you do some DDL, and you're off and playing. All right? Super easy, all right? Really well priced, in my opinion, and highly available, right? So 3 transactionally consistent replicas stored in the data center for you at any point in time. Key challenges with SQL Azure are the performance is highly non-deterministic. It is a very, very much a shared service because each of these replica servers is a shared server. And the performance you get is driven not only by how much load you're placing on your database, but how much load the people on all the other servers, right, are placing on their databases as well. So it's really hard to capacity plan for. Also has a limited database size of 150 gig. The reason for that is because we have these 3 replicas, we need to be able to deal with situations where a replica server fails, and we need to pick the database up and move it around the place. If your database is 7 or 8 terabytes in size, the process of getting a replica back up to serve your database can be very complex. There's a new thing called the premium SKU. Think of that as like reserved resources, buying 3 whole servers to serve up your database. It's actually really well priced, well worth going and having a look at $30 a day. Couple of sessions later today from Scott Klein that drill down into a whole lot more detail around SQL Azure. So, important concept. That should say SQL Azure. SQL Azure is the cheapest high availability relational database management system that money can buy. $5 a month it starts at. All right, I challenge anybody to do a high availability database for less than 2 or 3 orders of magnitude than that on premise or anywhere else. You just can't do it. Right? It's highly optimized to give you a high availability database for very, very little cache. Therefore, if you've got one of those nice simple scenarios, something like Windows Azure Websites and SQL Azure makes for a very, very awesome platform. Right? Really robust, durable platform for not much more than you'd pay for Bob's discount ASP.NET hosting. SQL Server and a IaaS virtual machine, right? So this is basically taking Windows Azure IaaS, taking Windows Azure disks, right? Attaching some disks, installing IaaS into that virtual machine. Gives you a whole lot of things that you can't get with Windows Azure SQL database, right? Transparent data encryption if you need to support HIPAA, right? US Health Information Protection Act, you're going to need transparent data encryption, right? You've got to be encrypted at rest. A whole lot of things that you can't get in SQL database, you can get in this because it is basically just bog standard SQL Server stuck in a Windows machine. Costs, you're going to pay for storage and watch those transaction costs, right? You're going to pay for your virtual machine time, and you potentially want to buy it with your SQL Server licenses bundled. Really good detailed performance tuning document at that link. And if you are running other types of databases in IaaS, it's worth going and having a look at that too, right? And because it's got some good tips for how do you optimize disk I/O for database type scenario. In terms of sort of working with it, it's worth doing load testing to do your capacity planning. It's a whole lot more deterministic and consistent in terms of its overall performance than Windows Azure SQL Database. Therefore, it is reasonably easy to capacity plan around. If you don't need massive scale, don't try and do massive scale. Stick with a single data disk and save yourself the pain of having to muck around and manage multiple disks. If you do need to increase performance, scale up. And I would lean towards using the high memory VM types, A6 and A7. Even as a high memory VM type, it's only going to give you 56 gigs of RAM, which to me feels like kind of light for a database workload, but it takes what you can get. And importantly, that gives you full rate network I/O off the machine, which you're going to want because all of your disk traffic is going over the network. You're going to want to use multiple drives, ideally using file groups to place files across those multiple drives. But if you really need more than 500 IOPS out of a single file, right, say tempDB or usually transaction logs, then you can combine multiple drives and spread that traffic over multiple drives. Don't use native operating system striping, do use storage spaces. And if you are still I/O bound, it's worth turning on data compression as well. For high availability, use always on availability groups, and you've got lots of options as to how you do that. You can do single data center HA, multi-data center HA, so HA between, say, Singapore and Hong Kong, or even HA between on-premise and the cloud. Right, so if you've got an on-premises database server, you could potentially do HA between your on-premises server and the cloud, wrap the whole lot in an Azure virtual network, and wham, bam, thank you, ma'am, you've suddenly got a really, really cool HA solution. Deep diving on this stuff, couple of sessions from North America TechEd. Just write down the session codes, you can go dig those up. Okay, that is the Microsoft stuff, and we have not a whole lot of time left, but that's okay. So I'm gonna jump over the stuff on the CAP theorem. You can go dig up the CAP theorem. Consistency, availability, partition tolerance. We're going to be most interested in talking about consistency and availability here. The meta message is it's really hard to scale distributed systems, right? And still be consistent, available, and partition tolerant, i.e. able to deal with situations where one part of the distributed system gets separated from another part of the distributed system. Let's drill through and keep talking about number 7. So number 7 is a thing called REAC. Who's heard of REAC? 1. Cool. REAC is like a really funky NoSQL key value store based around Amazon's Dynamo model. Right? It's got a full masterless design, which means that write availability can be guaranteed even if you only have a single node standing. It aims to be eventually consistent, preferring availability and partition tolerance. And basically what it lets you do is it lets you trade off in real time consistency and availability. So how consistent my data is versus how available the overall system is. And it does that by letting us tune these properties W and R, which are the number of nodes that must be written to by an operation before we return to the client, and the number of nodes that must return a consistent read before we return to the client. By tuning those two, we can provide strong consistency, i.e. when I write the data, if I go and read the data, I'm definitely going to get what I wrote back, right? And all the database people in the room are going, it's kind of, isn't that what a database is? Right? But no, actually, these things often sacrifice those strong consistency rules that you get with an ACID properties database. So if W plus R are greater than N, then we always get strong consistency. So for example, if we have 2 nodes, we must write to 2 before we return. Therefore, all of the nodes have the right data set. Therefore, when we read, we get the right data set back. If we have 4 nodes, right, the problem with that is any node failure, right, we can't write anymore. And this is optimized for availability, and it's really optimized for write availability. Right? So if we lose a node, it stops working. If n equals 4, w equals 3, r equals 2, we must write to 3 nodes, we must get consistent reads back from 2 nodes. That means we're always going to be reading the consistent copy of the data, but it can deal with a node failure. Right? So kind of nice the way we can sort of tune this to how we want it to work. I'm leaving aside the whole writes versus durable writes thing for the moment. We'll talk about durability in the next one. If we're less than n, then we're always going to be eventually consistent, right? If we've got 2 nodes, we must write to 1, we must read from 1. There will be a period of time where we can potentially read, right, the value from the server that has not been updated yet, right? That means we're eventually consistent. Setting W to 1 optimizes for write availability, R to 1 optimizes for read availability, but we can still be strongly consistent if we want, right? So if we've got 4 nodes and we set W to 1, as long as we set R, right, to N, we're always going to go and read all 4 nodes. And unless we get a consistent answer from all 4 nodes, we're not going to return to the client until we can get a consistent answer from all 4 nodes. Therefore, we ensure strong consistency while still assuring really, really strong write availability. And often that's what React is used to optimize for write availability. A few cool things that it's got pre and post commit hooks. So basically think of them like triggers. It's got pretty good indexing, much better than Windows Azure Table Storage, but doesn't have secondary indexes. It has Solr-like full-text search indexing. It has some MapReduce capabilities for doing some cool aggregate queries. In terms of sort of your pros and cons, I mean, it's classic NoSQL, so you've got to go and write an architecture application like it's a NoSQL application, which means that you kind of got to throw all your relational data modeling out the window. Doesn't have transactions. You're probably going to need to learn Erlang. Anyone know Erlang? No? Oh, one, maybe. Yeah, all good. It's kind of nice the way that model is tunable. Right, and that's tunable on a per request basis. Right, so you can tune for write availability on a per request basis. You can tune for read availability on a per request basis. If you like the look of Amazon DynamoDB, if you're moving from Amazon, right, and you're moving some stuff out of DynamoDB, running React's not a bad way to achieve that. Supported by Basho in Windows Azure by grabbing their CentOS-based VM from the MS OpenText VM depot. Who's used the MS OpenText VM depot? So just go to vmdepot.msopentext.com. MS OpenText is a subsidiary business of Microsoft focused on bringing open source technologies to the Microsoft platform. There's a whole load, like hundreds of VMs up there, all pre-configured and pre-built with open source software for sticking up in Windows Azure. Redis. So the question was asked before, hey, what's like the CDN for table storage? Well, the CDN for table storage is something probably a bit more like Redis, where durability is optional, right? So it's kind of a slightly different approach to databases where durability is optional. But yeah, Redis is focused on really, really high performance, and it does that by trading off durability, right? I.e. not writing the data to disk. And people are screwing their noses up going, are you kidding me? Not writing the data to disk, but actually it's kind of cool, right? It's eventually consistent. It uses master-slave replication, so the replication approach isn't quite as cool as React's replication approach. And it really is about trading off perf and durability. If you want it to be a fully durable database, right, with single node consistency, it can be by turning on what's called the append-only file. Again, it's a little bit like table storage where everything is written to that append-only file, and then we can rebuild the Redis cluster from those files should we have any outage. So to give you an interesting example, had a customer come to us. They built a SharePoint site, and it's mission critical, so it needs to be highly available. And occasionally they have these events, and they get a little bit of load, like not 10 times more traffic, 10 orders of magnitude more traffic than usual. And so at the moment they're spending some orders of magnitude of dollars on hosting, and it still falls over when they get the load. But Azure solves all these problems, doesn't it? Well, sort of, except the biggest database server I can have has 56 gigs of traffic and 8,000 IOPS, and actually I haven't got a shit show of serving that traffic off that. What can I do? All right, so they've got a pretty sophisticated setup here. So they've got dual data centers. Each data center's got failover clustering deployed. You can see where they're spending tens of thousands of dollars. They just can't deal with the load. All right. Nice thing is it's kind of a read-only site. So what we thought we'd do is we'd actually stick, who's heard of Nginx? Super high performance web server. Cool, pick up Nginx, right? Cache reverse proxy server. Okay, we'll do a cache reverse proxy server with Nginx, and then let's back our cache reverse proxy server with Redis, so we've kind of got a high performance in-memory cache that we can also persist to disk, so that if we have to reboot the caching server, we can go and pick the stuff up off disk rather than have to go and refetch it from SharePoint. And what do you know, I've now got this stateless caching reverse proxy tier that I can scale out till the cows come home, and only scale it out during those events, and suddenly I've solved this problem without having to go and touch this, and I've basically separated the two concerns. Scale is sorted, high availability, we can probably go and tweak this a little to try and reduce those overall hosting costs. Interesting approach. Anyone doing something like that yet? Yep. What are you guys, using a plain old reverse proxy server?
Well, we're serving a lot of our images
Yep.
through basically.
Yeah, it's really similar to the example I gave you before, right, with the CDN. If you've got stuff that's read-only, don't spend expensive clock cycles trying to serve it up out of, relational databases and expensive stuff. Stick it somewhere that's cheap, dish it out for cents on the dollar. Okay, Redis on Azure. Pretty easy to run it on Windows. If you want to run it on Linux and Azure, there's nothing in VM Depot yet, so you probably need to build your own image. Or you might use the Redis Cloud Managed Service from Guarantee. Important concept, all right? So that's that whole platform as a service, right? Buy it as platform as a service. Important concept. Great if you want to go and buy it as a platform as a service, right? But if what you're buying is a ultra high performance, ultra low latency data server, then round tripping to your platform as a service by going out of the load balancer into the load balancer, faffing around, hitting storage, back out of the load balancer, back into, it's kind of a waste of time, right? If really what you're buying is a really high performance, ultra low latency data server that you should probably be running on your web server nodes anyway. Right? I would not go buying Redis as a platform as a service, right? It's not designed to be consumed as a platform as a service. Go buy something much cooler, React, Mongo, lots of other options. Neo4j, anyone use a graph database? Anyone heard of a graph database? So graph database is, this is like a normal database, right? It's ACID compliant, transactional consistency. It looks just like a normal database, except it doesn't implement the relational model. It implements a graph model. So really good for really related data, right? That's hard to model in a relational database. I used to be very proud of how good I was at writing recursive stored functions to pull hierarchical data out of SQL Server. Anyone else also proud of their ability to write recursive stored functions to pull? Yeah. Ghastly, right? This stuff is really well suited for dealing with highly connected data. Social networks, recommendation engines, right? Good example here, path exists like you get in LinkedIn. So, do I know Steve in LinkedIn? Well, yeah, I kind of do through all these friends. 2,000 milliseconds in relational DB, 2 milliseconds in Neo4j, pretty much regardless of how big that graph actually happens to be. So that's kind of cool if you've got that sort of data. Running it on Azure, Neo4j have a pre-built cloud service package, CSPKG, that you can basically, off you go and slap it into Azure, or you can pick up the pre-built VM out of VM Depot if you want to run it on Linux. Your call. Number 10, I've got 5 minutes left, so we're doing really well. Elasticsearch is a distributed fancy pants search server, right? It picks up Lucene and it wraps it with a whole lot of cool logging, instrumentation, analytics, and other awesome, right? And basically builds your really cool search server. Full text indexing, wildcard searches, fuzzy searches, proximal searches, geospatial querying using distance-based queries, bounding boxes, the whole 9 yards. And then it just gives it to you as a RESTful interface that you can consume from your service. Squirt a JSON document into the search server, it gets indexed, go query the index, get JSON document back out. Kind of cool, yeah? Anyone using Lucene? Couple of people using Lucene, right? It's really well suited to that platform as a service type of consumption, right? So on Azure, no specific support yet, but there's a Stack Overflow thread there that looks to be being participated on by one of the key developers on the project, saying it's coming, but maybe not by the end of October. On Linux, you can obviously build your own VM, or you could probably go and poke around in the Amazon Web Services VM store, find one of their images and then do a VM conversion to run it. Or as platform as a service, there's a company called FacetFlow that looks to be bringing out a platform as a service offering. You can currently get a trial account with 5,000 documents for free. It's not in production yet that I can see. But I reckon this is pretty cool technology. If you've got to do anything that's got like full text searching and things in Azure, this to me is the way to do it, right? Even if you've got other database technologies sitting somewhere, extract some JSON from those, stick it into Elasticsearch or Solr and index it like that. So Solr is sort of the official Apache project that has some similar capabilities. I kind of like Elasticsearch a bit better. Anyone using Solr? Yeah. Right, 11, MongoDB is a document database. So it stores and indexes documents provided in the binary JSON format. So it's a binary representation of JSON. It's kind of like binary XML. All right, let's take a text representation and go, oh shit, this text is really, really large. Let's turn it into something a little bit more efficient. So it basically, you stick a BSON document in. It can index those. It's schemaless, so the documents don't have to look the same. It has server-side functions. It has MapReduce. It has master-slave replication, so it's consistent and available by default. It has geo-indexing. It has this really cool thing called GridFS. It's basically a distributed file system. You can stick a file in it, and it will push that file out across all the other nodes. So it kind of gives you a cool way of doing, again, that updatable distributed web server thing that I kind of think is a really common theme throughout this presentation, right? Distributed updatable web servers, stateless. Yeah, I really hate stateful stuff. That's why I do sessions on storage. Able to easily deal with really, really huge amounts of data. We're using this for a project at the moment where the JSON documents we're dealing with are effectively sort of log file documents, individual transactional log file documents coming off networking hardware, right? Where we expect the stuff to change over time. We're expecting to get huge amounts of data. So we can tune it for data volume and request load, and the data can change over time. Really elegant programming model, right? So it's just JSON documents, RESTful endpoint. So it could be kind of a cool thing. So I've seen the future in its client server. Remember the client server? Who are the VB guys? VB3. Yeah, cutting the teeth on VB3, right? In the case of sort of what goes around comes around, I reckon that one of the big app models we're going to start to see is what I call the new client server, which is basically to have some sort of pretty much untweaked, RESTful data server sitting in the cloud, front-ending it with a JavaScript and HTML-based application written using some sort of MVVM framework like Backbone, Knockout, Meteor, talking to that data. And if that doesn't look like a 1990s client server application to you, sure as hell looks like one to me, right? I reckon that's going to be a really popular app model in the next few years. So we'll see if it is, because I come back here each year, and if it doesn't, you can tell me I was wrong. So MongoDB on Azure, there's a clicky, draggy, droppy installer for VMs. You can stick it in a worker role using, and that's what we're using for the project we're working on at the moment. There's a pre-built Ubuntu image in VM Depot, and there's also a PaaS offering, and I'm sort of lukewarm on using it as a PaaS offering from the guys at Mongo Lab. And then the last one is kind of like, let's take all the previous 11 and stick them in the melting pot. And that is really to use a bunch of different stores, right? Every big application out there is using a bunch of different stores because every big application is probably using a relational database somewhere. Bugger off. All right. So, think of an e-commerce app. Everybody understands e-commerce. So what might that look like? You might have your financial transactions stuck in SQL Azure. You might stick your purchase, browse, and liking history into Neo4j that you can then use for some real-time interrogation for recommendation engines and so forth. You might actually be loading that using some sort of Hadoop-style big data pipeline. You probably put your sessions and shopping cart either in Redis or React because you want performance and you want guaranteed really strong write availability because you sure as shit don't want to stop the customer from adding stuff to their shopping cart. Right? You probably put your product catalog in either Mongo and or Elasticsearch, right? So it's really easy to search across. It's well suited because it's got, you can represent a product pretty easily as a JSON document, and then you stick your product images and blob storage, serve them out via the CDN. So important concept. Even if you're really into strong consistency, right? You just don't get this weak consistency model at all. As soon as you go to multiple data stores, right, you're probably going to have an eventually consistent system overall. So you kind of need to get your head around that. And with that, I've done pretty well, about bang on time, which is pretty good. We only have to skip a couple of slides. In terms of sessions you should go to, I highly recommend going to Steve's session, AZR 412 this afternoon, where you're going to go deep diving on table storage. Well worth going to for sort of higher level sort of concepts around NoSQL data modeling too. SQL Azure for the DBA, query tuning on SQL Azure, which I think is straight after this. If this stuff is just like totally blown your mind, you're going, wow, give me more. I highly recommend NoSQL Distilled by Martin Fowler, who's like the patterns and practices guy from way back, right? Which has got really good content on that sort of polyglot persistence model. And then I quite like the book 7 Databases in 7 Weeks, which basically does a bit of a lap around some but not all of the NoSQL data stores we've talked about today. If you want to talk to me, I'm going to the Intergen booth after I finish questions here, and we can hang out and drive racing cars and shoot the shit for a bit. Thank you all for coming along. Please do your evals. All feedback gladly accepted. Good feedback even more gladly accepted. Enjoyed running into you all, and have a great TechEd.